Hello, and welcome to The Sleepy Scientist. It's lovely to have you here. Before we begin, I'd love to know where in the world you're watching or listening from tonight. A quiet bedroom with the lights dimmed, a late-night train ride somewhere between cities, a comfortable sofa with a warm drink close by. Wherever you are, hopefully you're settled in, relaxed, and ready to drift gently into tonight's idea. If these calm explorations of science are something you enjoy, please consider liking the video and subscribing to the channel. It really helps this sleepy little corner of the universe continue drifting along. And to those already subscribed, thank you. Truly, your support means more than words can easily express. Now, tonight's topic might seem a little unusual, because the universe, when looked at carefully, is not the loud and chaotic place many people imagine. In fact, when astronomers measure the vast distances between stars and galaxies, something rather curious appears. The universe is incredibly quiet. Not quiet in the sense that nothing happens, far from it. Stars explode, galaxies collide, black holes swallow entire suns. But across the enormous emptiness of space, most of these dramatic events fade into something almost peaceful. From our tiny vantage point on Earth, the cosmos often appears calm, still, and strangely silent. It is as if the universe itself prefers quiet, which raises a rather interesting question. Why is the universe so quiet? On a clear night, the sky can feel almost impossibly calm. Stars hang quietly overhead, scattered across darkness like distant lanterns. They do not roar, flicker wildly, or rush across the sky. Instead, they appear steady, distant, and strangely patient. Even the brightest of them simply glows. For most of human history, this quiet view of the cosmos was all anyone had. And it gave rise to some very different ideas about what the universe was actually like. In ancient astronomy, the sky was not imagined as empty at all. It was often thought of as a carefully arranged structure, almost like a layered machine. The Greek philosopher Aristotle proposed that the heavens were composed of perfect celestial spheres, each one carrying planets and stars around the Earth in smooth circular motions. In this view, the cosmos was orderly, elegant, and packed with structure. The sky looked calm, yes, but it was assumed to be full. Medieval scholars inherited these ideas and expanded them. The heavens were believed to contain nested spheres made from a mysterious perfect substance called the quintessence. The moon moved within one sphere, the sun within another, and the distant stars were fixed to a final outer shell that slowly rotated around everything else. It was a universe that felt complete, almost architectural, but it was also very small. Even the most ambitious medieval thinkers imagined the cosmos as a structure not vastly larger than the solar system. The stars were distant, certainly, but not unimaginably so. There was no sense of the staggering scale that modern astronomy would eventually reveal. That revelation began slowly. The invention of the telescope in the early 1700s allowed astronomers to see the heavens in far greater detail. Suddenly the sky was not just a scattering of points of light. It contained clouds, clusters, and faint smudges of brightness that seemed to drift among the stars. At first, no one quite knew what these objects were. Some thought they were nearby gas clouds. Others suspected they were distant star systems. The uncertainty lingered for decades, quietly building toward one of the most important debates in the history of astronomy. In the early 20th century, two astronomers found themselves at the center of that debate, Harlow Shapley and Heber Curtis. Their disagreement, which became known as the Great Debate of 1920, focused on a deceptively simple question: How big is the universe? Shapley argued that the Milky Way galaxy was enormous, and that the mysterious spiral nebulae seen through telescopes were simply smaller clouds of gas within it. Curtis believed something far more dramatic. He suggested that those spiral shapes might be entire galaxies in their own right, vast collections of stars lying far beyond the boundaries of the Milky Way. At the time, both possibilities seemed plausible. The debate was not settled immediately. But within a few years, a quiet revolution arrived. An astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, began studying one of those spiral nebulae using the 100-inch Hooker telescope, which was then the most powerful telescope in the world. Hubble focused on a faint object known as the Andromeda Nebula. What he discovered changed everything. Within the hazy spiral shape, Hubble identified individual stars whose brightness varied in a predictable pattern. These stars belonged to a class known as Cepheid variables, whose true luminosity had been carefully studied by the astronomer Henrietta Swan Leavitt. Leavitt had discovered a remarkable relationship between the brightness of these stars and the time they took to brighten and dim. By measuring that cycle, astronomers could determine how intrinsically bright a Cepheid star actually was. Comparing that intrinsic brightness to how faint it appeared from Earth allowed its distance to be calculated. When Hubble performed that calculation for the stars in the Andromeda Nebula, the result was astonishing. The object was far beyond the boundaries of the Milky Way. It was not a nebula at all. It was an entirely separate galaxy. Suddenly the universe expanded from a single galaxy into a vast collection of them. Each galaxy contained billions of stars, and each one floated through immense stretches of space that separated it from its neighbours. The cosmos had just become incomprehensibly larger, and with that new scale came a new realization. Most of the universe was empty. This was not a small emptiness either. The distances between galaxies could stretch across millions of light years. Even within galaxies, stars were separated by enormous gulfs of space. Our own Sun, for example, lies about 4 light-years from the nearest star system, Alpha Centauri. That means light itself, travelling at the fastest speed known in nature, takes more than 4 years just to cross the gap. Between those stars lies almost nothing, just a faint scattering of atoms drifting through the interstellar medium. This realization led to a profound shift in how astronomers thought about the cosmos. The universe was not a tightly packed machine of celestial spheres. It was something far stranger, a vast structure made mostly of emptiness. Cosmologist Edward Harrison later reflected on this idea while studying the large-scale structure of the universe. Harrison pointed out that the apparent quietness of the cosmos does not mean that little is happening. Instead, it reflects the geometry of space itself. Matter gathers into galaxies and clusters under the influence of gravity, while the space between them stretches across enormous distances. The result is a universe that appears calm when viewed from afar. But that calmness is deceptive. Inside galaxies, stars are constantly forming within dense clouds of gas. Elsewhere, massive stars explode in supernovae powerful enough to briefly outshine entire galaxies. Black holes swallow matter, neutron stars collide, and streams of radiation burst across intergalactic space. Yet across the scale of the universe, these events are separated by such vast distances that the cosmos still feels quiet. This idea fascinated the theoretical physicist John Archibald Wheeler. Wheeler spent much of his career thinking about the deep structure of reality, from black holes to quantum mechanics. One question he often returned to was deceptively simple. Why does a universe capable of such extraordinary energy appear so calm when observed from afar? Why does the night sky feel peaceful rather than chaotic? Part of the answer lies in the sheer scale of the cosmos. When events are separated by millions or billions of light years, they rarely overlap from our perspective. Each one becomes an isolated flicker in the distance rather than part of a constant cosmic storm. But another part of the answer lies in the nature of space itself. Because the quietness of the universe is not only about distance, it is also about silence. The vast emptiness between stars and galaxies does something remarkable. It prevents most forms of vibration from travelling across the cosmos. The explosions of distant stars do not roar through space the way thunder rolls through Earth's atmosphere. Instead, they unfold in near-perfect silence, which raises a curious thought. Perhaps the universe is not truly quiet because little is happening. Perhaps it simply lacks the conditions needed for us to hear it. And understanding that idea begins with the simple question: what exactly is sound? To understand why the universe feels so quiet, it helps to begin with something familiar: sound. On Earth, sound is everywhere. The rustle of leaves, the hum of distant traffic, the gentle tapping of rain against a window. Even in places that feel peaceful, the air is usually filled with tiny vibrations moving quietly from one place to another. But sound is not simply a thing that exists on its own. It is a process. At its most basic level, sound is a mechanical vibration traveling through matter. When something moves or strikes another object, it causes nearby particles to jostle back and forth. These movements pass from particle to particle in a chain reaction, spreading outward like ripples across water. That travelling ripple is what the human ear detects as sound. Air carries these vibrations extremely well. When someone speaks, the vocal cords push air molecules forward and backward in rapid pulses. Those pulses move outward through the atmosphere, eventually reaching another person's ears where they're converted into electrical signals by the auditory system. Water can carry sound too. In fact, sound moves even faster through water than it does through air, which is why whales can communicate across enormous distances beneath the ocean surface. Solid materials can transmit vibrations as well. If someone presses an ear against a railway track, the rumble of an approaching train can sometimes be heard long before it becomes audible in open air. In all of these cases, something important is present: matter. Sound needs particles. It requires atoms or molecules close enough together that they can bump into one another, passing energy along step by step. Without those particles, the vibration simply has nothing to push against. This idea may seem obvious today, but there was a time when scientists were not entirely certain how sound behaved in empty space. In the 17th century, natural philosophers began experimenting with ways to create artificial vacuums, attempting to remove air from sealed containers. One of the earliest pioneers in this area was the German scientist Otto von Guericke. Von Guericke is remembered for a dramatic demonstration involving two large metal hemispheres that had been fitted together and evacuated of air. Teams of horses attempted to pull the hemispheres apart but failed, revealing just how powerful atmospheric pressure could be. But von Guericke also explored a quieter question: what happens to sound when air is removed? His experiment suggested that sound weakened dramatically in a vacuum. Later scientists refined these tests, including the English chemist and physicist Robert Boyle. Boyle placed a ringing bell inside a glass chamber and gradually pumped out the air. As the air disappeared, the bell continued to vibrate, but its sound faded until it became nearly impossible to hear. The bell was still, ringing. But the sound had nowhere to go. These early vacuum experiments helped establish one of the key principles of acoustics. Sound requires a medium through which vibrations can travel. Remove the medium, and the vibrations remain trapped at their source. Later scientists expanded this understanding by studying how vibrations move through different materials. In the 18th century, the German physicist Ernst Chladni conducted elegant experiments with vibrating plates. By sprinkling fine sand across metal plates and then drawing a violin bow along the edges, Chladni caused the plates to vibrate in specific patterns. The sand gathered into intricate geometric shapes that revealed how sound waves moved across the surface. These patterns, now known as Chladni figures, provided one of the earliest visual demonstrations of wave behavior in solid materials. A century later, Hermann von Helmholtz deepened the scientific understanding of acoustics by studying how sound waves interact with the human ear and with physical objects. Helmholtz showed that sound could be analyzed mathematically as oscillating pressure waves moving through matter. Put simply, sound is motion passed from particle to particle, which brings us to space. The environment between the stars is almost unimaginably empty. On Earth, even the cleanest air contains billions upon billions of molecules in every small volume. In contrast, the space between stars contains only a few atoms per cubic centimetre, sometimes fewer. This thin scattering of gas is known as the interstellar medium, a term widely studied by the astrophysicist Lyman Spitzer during the 20th century. Spitzer helped reveal that although space appears empty, it does contain faint traces of hydrogen gas, dust grains, and ionized particles drifting through the galaxy. But the key word here is faint. The particles are so widely separated that they rarely interact with one another. Imagine standing in a room where the nearest person is several kilometers away. Passing a vibration along a chain of people would become nearly impossible. That is essentially the situation in interstellar space. Even if a star explodes in a spectacular supernova, sending shock waves racing outward at tremendous speeds, those waves quickly thin out as they spread into the near vacuum surrounding them. The particles are simply too far apart to transmit a continuous sound wave across large distances. The explosion would still release enormous energy, but it would unfold in silence. This silence does not mean that nothing moves through space. Quite the opposite. Space is filled with other forms of energy that travel in very different ways. Light, for example, can cross the vacuum of space without difficulty, because electromagnetic radiation does not require a material medium. It moves through the fabric of space itself, carrying energy and information across immense distances. There are also more exotic forms of motion present in cosmic environments, in regions where gas becomes ionized, meaning the atoms lose some of their electrons, the particles become electrically charged. Charged particles respond strongly to magnetic fields, and their behavior can produce complex patterns of motion, known as plasma waves. These phenomena were explored in detail by the Swedish physicist Hannes Alfvén, who developed the field of magnetohydrodynamics. This branch of physics studies how electrically conducting fluids, such as plasma, interact with magnetic fields. Alfvén showed that in certain cosmic environments, waves can travel through ionized gas along magnetic field lines, transferring energy across space in ways that resemble sound, but are governed by electromagnetic forces. These plasma waves are fascinating, but they are not sound in the everyday sense. They occur under very specific conditions and do not propagate through the vast majority of interstellar space. For ordinary sound, the requirement remains simple. Particles must be close enough together to pass vibrations along. In space, they usually are not. This is why astronauts floating outside a spacecraft cannot hear an explosion nearby unless the vibration travels through the structure of the spacecraft itself. The surrounding vacuum provides no pathway for the sound to reach them. The universe, in that sense, is profoundly quiet, not because events do not occur, but because the environment between those events prevents vibrations from travelling freely. Yet the silence of space is only part of the story. Even more striking than the vacuum itself are the enormous distances that separate the stars. Distances so vast that entire solar systems drift through the galaxy without ever coming close to one another. And once those scales are considered, the quietness of the universe begins to feel less surprising. It begins to feel inevitable. Once the silence of space is understood, another feature of the universe begins to stand out even more clearly: distance. Not the ordinary kind experienced on Earth, where cities lie a few hundred kilometers apart and oceans span a few thousand. The distances between stars are of an entirely different scale, so vast that human intuition struggles to picture them accurately. The nearest star system to Earth, known as Alpha Centauri, lies a little more than 4 light-years away. That means light, which moves faster than anything else known in nature, takes more than 4 years to travel from that star to our planet. 4 years, and that is the closest one. Within the Milky Way galaxy there are hundreds of billions of stars, yet they are separated by enormous gulfs of space. Our solar system occupies a tiny gravitational bubble around the Sun, and even that bubble stretches for trillions of kilometers before the Sun's influence begins to fade. Beyond that boundary lies a dark region of interstellar space that continues for years of light travel before another star system appears. If the Sun were shrunk to the size of a small coin resting on a table, the nearest star would still be thousands of kilometers away. It is no exaggeration to say that stars drift through a galaxy that is mostly empty. For centuries, however, astronomers had no reliable way to measure these staggering distances. The stars looked like tiny points of light in the sky, and without a sense of depth, it was nearly impossible to know how far away they truly were. The breakthrough arrived during the early 19th century through the careful work of the German astronomer Friedrich Bessel. Bessel used a technique known as stellar parallax, which relies on the motion of Earth around the Sun. As Earth travels along its orbit over the course of a year, nearby stars appear to shift slightly against the background of more distant stars. It is a very small shift, so small that detecting it required years of careful observation and extremely precise instruments. In 1838, Bessel successfully measured the parallax of a star known as 61 Cygni. From that tiny shift in position, he calculated the star's distance from Earth. For the first time in history, humanity had a reliable measurement of the distance to another star. The result confirmed what some astronomers had long suspected: the stars were unimaginably far away. As the 19th and early 20th centuries progressed, astronomers began cataloguing stars in greater detail. Observatories around the world mapped their brightness, colours, and spectral signatures. These observations slowly revealed that stars were not random points scattered through space, but part of a vast population distributed across the Milky Way. One of the astronomers who contributed significantly to this work was Annie Jump Cannon at the Harvard College Observatory. Cannon developed a classification system that organized stars according to their spectral characteristics, effectively sorting them by temperature. Her system, still used today, revealed that stars come in distinct categories ranging from extremely hot blue stars to cooler red ones. This classification helped astronomers understand how stars differ from one another and how they are distributed throughout the galaxy. Another key figure in this growing understanding was Cecilia Payne-Gaposchkin. In the 1920s, Payne-Gaposchkin analyzed stellar spectra and made a remarkable discovery. She demonstrated that stars are composed primarily of hydrogen and helium, overturning earlier assumptions that their composition resembled Earth. Her work revealed that stars share a common chemical foundation, suggesting that the galaxy itself formed from vast clouds of gas that eventually condensed into individual stellar systems. Each of those systems then evolved largely on its own. This idea was later explored in depth by the astrophysicist Subrahmanyan Chandrasekhar, who studied the physical limits governing stellar structure. Chandrasekhar showed that stars are held in balance by a competition between gravity pulling inward and pressure from nuclear fusion pushing outward. This balance allows stars to remain stable for extremely long periods. Many stars live for billions of years without dramatic changes in brightness or motion. They burn quietly, slowly converting hydrogen into helium within their cores. In other words, once stars form, they tend to settle into long, stable lives. This stability contributes to the calm appearance of the galaxy. Even though stars contain immense energy, most of that energy is released gradually over millions or billions of years. There are exceptions, of course. Some stars eventually explode in supernova events, releasing enormous bursts of energy. But these explosions are rare when viewed across the entire galaxy. Most stars simply glow steadily in the darkness. Another important insight into stellar spacing came from careful observations of star distributions across the sky. Among the many observers who contributed to this effort was the Indian astronomer Radha Gobinda Chandra. Working largely with modest equipment, Chandra spent years observing variable stars and tracking their brightness over time. His work, along with that of other dedicated observers around the world, helped astronomers build a clearer picture of how stars populate the Milky Way. What emerged from these observations was the concept of stellar neighborhoods. Stars are not evenly scattered like grains of sand. Instead, they often form loose groups or clusters that share similar origins. Some clusters contain hundreds or thousands of stars bound together by gravity. But even within these groups, the distances between individual stars remain immense. Gravity holds the cluster together, yet the stars themselves rarely come close enough to interact directly. In fact, direct collisions between stars are extraordinarily rare events. Consider our own Sun as an example. As it orbits the center of the Milky Way, it travels through the galaxy at a speed of roughly 200 kilometers per second. Over millions of years, it passes through different regions of space and occasionally moves near other stars. Yet the distances involved are so great that these encounters almost never lead to collisions. Stars simply glide past one another, like ships drifting across a vast and nearly empty ocean. This spacing has profound consequences for the appearance of the universe. Because stars are so widely separated, their light reaches us individually rather than blending into a constant glow. Each star becomes a single point of brightness against the night sky, surrounded by enormous regions of darkness. If stars were packed more closely together, the sky would look very different. The darkness between them would shrink, and the heavens might appear filled with continuous light. Instead, the galaxy resembles a sparse archipelago of stars floating in a sea of emptiness. This separation also contributes to the quietness of the cosmos. Events occurring around one star system rarely influence another. A supernova explosion in a distant region of the galaxy may unleash staggering amounts of energy, but by the time its radiation spreads across the vast gulf separating stars, it becomes faint and diffuse. The universe is active, but it is active at a distance, and that distance softens everything. The result is a galaxy that appears calm even while enormous physical processes unfold within it. Yet the Milky Way itself is only one example. When astronomers step back and look at galaxies as a whole, they discover something even more surprising. Entire galaxies are also separated by immense regions of empty space. When the immense distances between stars become clear, another realization begins to take shape. The galaxy itself is also mostly empty. From Earth, the Milky Way appears as a faint river of light stretching across the night sky. Under truly dark conditions, far from city lights, it can look almost like a misty cloud arching overhead. For many centuries it was simply called the Milky Way because of this soft milky glow. But that glow hides an enormous structure. The Milky Way is a spiral galaxy, a vast rotating system of stars, gas, dust, and dark matter bound together by gravity. Its visible portion stretches roughly 100,000 light-years from one side to the other, forming a broad, flattened disk that slowly rotates through space. And within that disk are hundreds of billions of stars. That number sounds crowded, yet the reality is quite the opposite. Those stars are scattered across such enormous distances that even the dense regions of the galaxy contain far more empty space than matter. Most stars drift through regions where their nearest stellar neighbours remain several light-years away. The galaxy is immense, but the emptiness inside it is even greater. Spiral galaxies like the Milky Way share a common structure that astronomers have studied for decades. At the centre lies a dense region known as the galactic bulge, where stars gather more closely together around a supermassive black hole. Surrounding this bulge is the galactic disk, a wide rotating plane that contains most of the galaxy's stars. Threaded through that disk are the famous spiral arms. These arms are not rigid structures like the blades of a fan. Instead, they are regions where gas and stars become slightly more concentrated as they orbit the galactic center. Over time, waves of density move through the disk, compressing clouds of gas and triggering the birth of new stars. The result is a galaxy with glowing spiral patterns that appear almost like cosmic whirlpools. Beyond the disk lies another component known as the galactic halo. This region extends far above and below the galaxy's main plane and contains scattered stars, ancient globular clusters, and a mysterious form of matter that cannot be seen directly. Dark matter. The existence of dark matter became clear during the 1970s through the work of the American astronomer Vera Rubin. Rubin carefully measured how stars move within spiral galaxies by studying their rotation curves, which describe how orbital speed changes with distance from the galactic center. According to classical gravitational physics, stars farther from the center of a galaxy should orbit more slowly. The visible mass of the galaxy should not provide enough gravity to keep them moving quickly. But Rubin found something unexpected. Stars at the outer edges of galaxies were orbiting just as fast as those closer to the center. This observation suggested that galaxies contain far more mass than what can be seen in stars and gas alone. The extra gravity had to be coming from something invisible, a substance that does not emit light but still exerts gravitational influence. This invisible component became known as dark matter. Rubin's observations transformed the way astronomers think about galaxies. It now appears that most of a galaxy's mass exists in an enormous halo of dark matter surrounding the visible disk, and that halo extends far beyond the regions filled with stars. The idea that galaxies contain hidden mass had actually been proposed decades earlier by the Swiss astronomer Fritz Zwicky. In the 1930s, Zwicky studied clusters of galaxies and noticed that the galaxies within those clusters were moving far too quickly to be held together by visible matter alone. He concluded that some form of unseen matter must be present, adding gravitational strength to the system. Zwicky referred to this mysterious substance as dark matter. At the time, the idea received little attention, but later observations, including Rubin's rotation curve measurements, strongly supported the concept. Today, dark matter is considered one of the central components of cosmic structure. It shapes the formation of galaxies, influences their motion, and helps explain why these vast systems remain stable over billions of years. Even so, the presence of dark matter does not make galaxies crowded. Far from it. The stars themselves occupy only a tiny fraction of the total volume within a galaxy. Astronomers studying galactic dynamics have long worked to understand how these stars are distributed and how they move collectively through space. One important contribution came from the American astronomer Sandra Faber, who helped develop what is known as the Faber-Jackson relation. This relationship links the brightness of certain galaxies with the velocities of the stars moving inside them. By studying these motions, astronomers can estimate the mass and internal structure of galaxies, revealing how gravity organizes their enormous populations of stars. The results consistently point to the same conclusion. Galaxies are vast systems, but they are remarkably sparse. Most of their volume contains little more than drifting gas and faint dust particles. The stars themselves remain widely spaced, orbiting the galactic center like distant islands in a cosmic ocean. Understanding how galaxies form also reveals why this emptiness persists. Modern cosmology suggests that galaxies did not appear all at once. Instead, they grew gradually through a process known as hierarchical merging. In this scenario, small clumps of matter formed first in the early universe, eventually merging together under gravity to build larger and larger structures. Cosmologists such as Simon White and Carlos Frenk helped develop detailed computer simulations showing how this process might unfold over billions of years. Their models demonstrated that dark matter plays a crucial role in guiding galaxy formation, providing the gravitational framework within which gas can gather and form stars. As galaxies assemble through mergers and accretion, their stars spread out across enormous regions of space. The result is a structure that is massive but extremely diffuse. Even a galaxy containing hundreds of billions of stars still leaves most of its volume unoccupied. The distances between stars remain so large that direct collisions are extraordinarily rare. Entire solar systems can orbit the galaxy for billions of years without ever encountering another. This vast spacing also explains why galaxies appear calm when viewed from afar. Within any given galaxy, dramatic events do occur. Massive stars collapse into neutron stars. Supernova explosions release staggering bursts of energy. Black holes consume surrounding matter and unleash powerful jets of radiation. Yet these events are scattered across distances measured in thousands or even tens of thousands of light years. Each one becomes an isolated flicker of activity rather than part of a continuous cosmic storm. The galaxy, taken as a whole, appears peaceful. It is a quiet archipelago of stars drifting through a sea of darkness. And the Milky Way is only one example among many. Across the observable universe there are hundreds of billions of galaxies, each one separated from its neighbors by immense stretches of space. When astronomers map these galaxies across the sky, they discover that even galaxies themselves are not evenly distributed. They gather into clusters and filaments, leaving enormous regions where very little matter exists at all. These immense structures form a pattern that stretches across the entire universe, a pattern sometimes described as the cosmic web. An understanding that web reveals an even deeper layer of cosmic emptiness. When astronomers first began mapping galaxies across the sky, they expected something relatively simple. Perhaps galaxies would be scattered randomly, like grains of sand tossed across a surface. Or perhaps they would spread out smoothly in all directions, forming a gentle cosmic fog of stars and galaxies drifting through space. But the universe had something far more interesting in mind. As larger and more detailed surveys of the sky began to appear during the late 20th century, astronomers noticed that galaxies were not distributed evenly at all. Instead, they gathered into clusters, chains, and enormous curved structures stretching across the universe. Between these structures lay enormous regions containing almost nothing. This grand pattern is now known as the cosmic web, and once seen, it becomes impossible to forget. Imagine looking at the universe from far beyond the boundaries of the Milky Way. Instead of a smooth cloud of galaxies, you would see something resembling a vast three-dimensional network. Long filaments of galaxies stretch across space, connecting dense clusters like strands of glowing thread. These filaments weave together into an intricate lattice that extends across the observable universe. In between those strands lie enormous empty regions called cosmic voids. The structure resembles a sponge, or perhaps the delicate foam of bubbles on the surface of water, except the bubbles are hundreds of millions of light years across. This extraordinary architecture did not emerge as a surprise to everyone. Decades before astronomers had the observational tools to map galaxies across such enormous distances, a Soviet physicist named Yakov Zeldovich had already begun to suspect that the universe might organize itself into filamentary structures. Zeldovich studied how gravity influences the growth of matter in the expanding universe. His work focused on what happens when tiny variations in density begin to grow under the influence of gravitational attraction. Even in the early universe, matter was not perfectly uniform. Some regions were slightly denser than others. Those slightly denser regions exerted a little more gravitational pull, drawing in surrounding matter over time. This process is known as gravitational instability. Over millions and then billions of years, these small irregularities gradually grew larger. Zeldovich predicted that as matter collapsed under gravity, it would not gather into perfectly spherical clusters. Instead, it would collapse first into sheets, then into filaments, and finally into dense nodes where filaments intersect. These nodes would eventually become clusters of galaxies. For many years, this idea remained largely theoretical. Observing the large-scale structure of the universe required mapping galaxies across vast regions of space, something that earlier telescopes and surveys could not easily accomplish. That situation changed dramatically toward the end of the 20th century. Large collaborative projects began to measure the positions and distances of hundreds of thousands and eventually millions of galaxies. One of the most influential of these efforts was the Sloan Digital Sky Survey, an ambitious astronomical project that began mapping the universe in the early 2000s. Using a dedicated telescope located at Apache Point Observatory in New Mexico, the Sloan Digital Sky Survey recorded the positions and spectral properties of enormous numbers of galaxies. By measuring how their light was shifted toward the red end of the spectrum through a process known as cosmological redshift, astronomers could determine how far away those galaxies were. With these measurements, they began constructing three-dimensional maps of the universe. What those maps revealed was breathtaking. Galaxies were not scattered randomly. They were arranged along immense filaments stretching across hundreds of millions of light years. These filaments intersected at dense nodes where clusters of galaxies gathered under powerful gravitational forces. Between them were vast empty spaces. Later observational efforts such as the Dark Energy Survey expanded these maps even further, capturing images of hundreds of millions of galaxies across large portions of the sky. These surveys allowed astronomers to trace the cosmic web in ever greater detail, confirming the large-scale structure predicted by Zeldovich decades earlier. The universe, it seemed, truly was woven like a vast cosmic net. Within this net, some of the most intriguing regions are the cosmic voids. These voids are immense volumes of space containing very few galaxies. In some cases, they stretch across hundreds of millions of light years, while holding only a handful of scattered galaxies. Compared with the dense filaments of the cosmic web, these regions are almost completely empty. Astronomers have studied these voids carefully in order to understand how matter is distributed throughout the universe. One of the researchers who helped clarify our place within this vast structure is Brent Tully, an astronomer known for his work on large-scale galaxy motions. Tully and his collaborators identified a massive region of interconnected galaxy clusters known as the Laniakea supercluster. The name Laniakea comes from a Hawaiian phrase meaning immense heaven, a fitting description for such a colossal structure. The Milky Way galaxy resides within this enormous gravitational basin, which contains roughly 100,000 galaxies moving slowly toward a common center of gravitational attraction. Yet even a structure as large as Laniakea occupies only a small portion of the surrounding cosmic landscape. Beyond its boundaries lie enormous voids where galaxies become increasingly scarce. Some of these voids are so large that light itself takes hundreds of millions of years to cross them. Inside them, matter is spread so thinly that entire regions of space contain almost no galaxies at all. The universe, on its largest scales, resembles a delicate lacework of matter suspended across enormous distances. Understanding why this structure forms requires returning to the role of gravity. Gravity is a remarkable force because it acts over unlimited distances. Even small concentrations of matter can gradually pull surrounding material toward them over time. When the universe was young, tiny fluctuations in density began to grow through this gravitational attraction. Denser regions slowly gathered more material, while less dense regions gradually lost matter to their surroundings. Over billions of years, this process amplified itself. Matter flowed toward the growing filaments and clusters, leaving behind vast underdense regions that became cosmic voids. The more matter gathered into filaments, the emptier the surrounding regions became. In this way, the architecture of the universe naturally created enormous volumes of quiet emptiness. The cosmic web is therefore not just a visual curiosity. It is a direct consequence of the laws of gravity acting over immense spans of time and space. Clusters of galaxies form the glowing intersections of this web. Filaments stretch outward like cosmic highways connecting these clusters, and between them lie vast regions where almost nothing exists at all. These voids represent some of the most peaceful regions in the universe. Few galaxies reside there. Few energetic events occur. The darkness inside them is profound, interrupted only by faint light from distant structures far beyond their boundaries. It is within this enormous architecture that the quietness of the cosmos becomes most obvious. The universe is not merely empty in small patches. Its emptiness is built into the very geometry of cosmic structure. Matter gathers along filaments and nodes, leaving immense regions of silence between them. The largest structures in existence therefore create the largest spaces where almost nothing happens. A cosmic stillness written into the architecture of the universe itself. Yet this raises an even deeper question. If the cosmic web emerged from tiny fluctuations in matter, where did those fluctuations come from in the first place? To answer that, the story must travel much farther back in time, back to the earliest moments of the universe itself. The quiet universe seen today did not always exist in this calm state. In fact, if someone could travel far enough back in time, the cosmos would appear almost unimaginably different. The vast emptiness between galaxies, the gentle glow of distant stars, and the slow drifting of cosmic structures would give way to something far more energetic. The early universe was not quiet at all. It was dense, hot, and filled with radiation. Shortly after the beginning of cosmic expansion, the entire observable universe existed in a state where matter and energy were compressed together at extraordinary temperatures. Instead of galaxies and stars, space contained a turbulent mixture of elementary particles, radiation, and plasma. Photons, electrons, and protons interacted constantly, colliding and scattering in every direction. The universe at that time behaved less like a calm cosmic landscape and more like a blazing ocean of energy. Understanding how scientists came to this conclusion begins with a remarkable idea proposed during the early 20th century by the Belgian physicist and priest, Georges Lemaitre. Lemaitre suggested that the universe was not static or eternal in its present form. Instead, he proposed that it had expanded from a much smaller and denser state in the distant past. In 1927, Lemaitre described a universe that was gradually stretching over time, with galaxies moving away from one another as space itself expanded. He referred to the original state of the universe as the primeval atom, imagining all matter once compressed into a single, extremely dense beginning. This idea eventually became known as the Big Bang theory. At first, the concept was controversial. Many scientists preferred a static universe that had always existed. Even Albert Einstein initially resisted the notion of cosmic expansion, although he later acknowledged that the mathematical framework of general relativity allowed for such a possibility. Evidence for an expanding universe grew steadily as observations improved. Astronomers discovered that distant galaxies appear to move away from Earth, and the farther a galaxy lies, the faster it appears to recede. This pattern revealed that the fabric of space itself was stretching. If the universe is expanding today, then logically it must have been smaller in the past. Continue tracing that expansion backward far enough, and the universe reaches an earlier epoch when matter and radiation were compressed together into a hot, dense state. In that environment, energy filled every region of space. Particles collided constantly. Radiation scattered through the dense plasma. The universe behaved like a glowing cosmic furnace. This early period left behind a remarkable relic that astronomers would discover many billions of years later. In the 1960s, two radio astronomers named Arno Penzias and Robert Wilson were working with a sensitive microwave antenna at Bell Laboratories in New Jersey. They were studying faint radio signals from the sky when they encountered a persistent background noise that seemed to come from every direction. At first, they suspected a technical problem. They carefully checked the instrument, cleaned the antenna, and even removed nesting pigeons that had taken up residence inside the equipment. Yet the mysterious signal remained. Eventually they realized that the noise was not a malfunction at all. It was coming from the universe itself. What Penzias and Wilson had detected was the cosmic microwave background radiation. the faint afterglow of the early universe. This radiation originated roughly 380,000 years after the beginning of cosmic expansion, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, photons constantly scattered off free electrons in the dense plasma, preventing light from travelling freely. Once atoms formed, the universe became transparent to radiation, allowing photons to stream through space for the first time. Those ancient photons are still travelling today. Over billions of years, cosmic expansion stretched their wavelengths into the microwave region of the electromagnetic spectrum. What remains is an extremely faint radiation field that fills all of space. It is the oldest light that can be observed. But this ancient glow also contains subtle patterns. When astronomers studied the cosmic microwave background in greater detail, using satellites such as the Cosmic Background Explorer, and later the Wilkinson Microwave Anisotropy Probe and the Planck Observatory, they discovered tiny variations in temperature across the sky. These fluctuations were incredibly small, yet they carried profound meaning. They revealed that the early universe was not perfectly uniform. Some regions were slightly denser than others. These small differences in density served as the seeds from which galaxies and galaxy clusters eventually formed. Gravity slowly amplified these fluctuations, pulling matter into growing structures across billions of years. The early universe was therefore filled with ripples, not only in matter, but in sound. During the first several 100,000 years after cosmic expansion began, the universe consisted of a hot plasma of electrons, protons, and photons. In this environment, pressure from radiation pushed outward, while gravity pulled matter inward. This balance created oscillations in the plasma. Regions of slightly higher density would collapse under gravity, compressing the plasma. Radiation pressure would then push outward again, causing the region to expand. The result was a series of rhythmic waves moving through the early universe. These waves are known as baryon acoustic oscillations. Although they occurred in an extremely hot plasma rather than in ordinary air, the physical principle was remarkably similar to sound waves. Pressure and gravity created oscillations that propagated through the dense medium of the young universe. Cosmologists such as Daniel Eisenstein have studied these oscillations carefully because they left a measurable imprint on the distribution of galaxies across cosmic space. The spacing between large-scale structures today still reflects the pattern created by those ancient waves. In other words, the large-scale structure of the universe still carries the memory of sound waves that travelled through the primordial plasma. Another fascinating interaction between radiation and matter was described by the astrophysicist Rashid Sunyaev. Working with Yakov Zeldovich, Sunyaev studied how the cosmic microwave background radiation interacts with clusters of galaxies. When ancient microwave photons pass through the extremely hot gas inside a galaxy cluster, they can gain energy by scattering off energetic electrons. This process slightly alters the energy distribution of the background radiation. The effect is now known as the Sunyaev-Zeldovich effect. Astronomers use this phenomenon as a powerful observational tool to study galaxy clusters and trace large-scale structures across the universe. It provides yet another reminder that the early universe was a place of intense interactions between radiation and matter, a place filled with motion, filled with energy, filled with sound like oscillations moving through cosmic plasma. Over time, however, the universe expanded. As space stretched outward, matter became more widely separated. The density of particles gradually decreased, and the intense interactions that once filled every region of space began to fade. The cosmic furnace slowly cooled. The plasma cleared. radiation thinned, and the universe began its long transition from a noisy, energetic beginning toward the quiet, spacious cosmos seen today. A transformation shaped by the expansion of space itself. As the early universe cooled and matter gradually gathered into the first stars and galaxies, another process continued quietly in the background. Space itself was expanding. This idea may sound abstract, at first, because it does not behave like an ordinary explosion. When something explodes on Earth, fragments are thrown outward through space. But the expansion of the universe is different. It is not galaxies moving through empty space away from a single central point. Instead, the space between galaxies is stretching. Every large region of the universe slowly grows larger over time, carrying galaxies farther apart from one another. The galaxies themselves are not flying through a static cosmic landscape. Rather, the fabric of space between them is gradually expanding. This concept began to take shape through the work of several scientists during the early 20th century. One of the most important theoretical contributions came from the Russian physicist Alexander Friedmann. In 1922, Friedmann examined the equations of general relativity developed by Albert Einstein and discovered something remarkable. Einstein's theory did not require the universe to remain static. In fact, Friedmann showed that the equations naturally allowed for a universe that either expanded or contracted over time. His solutions described how the geometry of space-time could evolve depending on the amount of matter and energy present. At the time, this idea seemed radical. Most scientists still imagined the cosmos as a fixed and eternal structure. Even Einstein had initially introduced a mathematical adjustment to his equations, known as the cosmological constant, in order to maintain a static universe. But the universe itself soon provided evidence that Friedmann's expanding solutions were correct. In the late 1920s, the astronomer Edwin Hubble carefully measured the light from distant galaxies at the Mount Wilson Observatory. By studying their spectra, he noticed that many galaxies exhibited a shift toward longer wavelengths of light. This phenomenon is known as redshift. When light from an object stretches toward the red end of the spectrum, it indicates that the object is moving away from the observer. The same effect can be heard with sound when a passing siren changes pitch as it moves past, a phenomenon known as the Doppler effect. Hubble discovered that galaxies were not only moving away from Earth, but that the speed of their recession increased with distance. The farther a galaxy appeared, the faster it seemed to be moving away. This relationship became known as Hubble's law. In simple terms, it states that the recessional velocity of a galaxy is proportional to its distance from the observer. The more distant the galaxy, the greater the redshift observed in its light. The underlying principle can be expressed in a compact mathematical form often written in physics as velocity equals the Hubble constant multiplied by distance. Although the equation itself is concise, its implications are enormous. If galaxies appear to be moving away from one another in every direction, the most natural explanation is that space itself is expanding. Just as dots drawn on the surface of an inflating balloon move farther apart as the balloon expands, galaxies become more widely separated as the universe grows larger. This expansion occurs everywhere at once. No single point in space serves as the center. From the perspective of any galaxy, all distant galaxies appear to be moving away in the same general pattern. Each observer sees themselves surrounded by a universe that is gradually stretching outward. Over billions of years, this expansion has had profound consequences for the structure of the cosmos. Galaxies that once formed relatively close groups slowly drift farther apart. Clusters of galaxies become more isolated from one another. The distances between large cosmic structures continue to grow as space itself expands. The universe becomes more spacious with time, and with greater distance comes greater quiet. When galaxies lie millions of light years apart, interactions between them become increasingly rare. The gravitational influence of one galaxy on another weakens with distance, and collisions between galaxies occur only occasionally across cosmic timescales. Most galaxies simply travel along their paths through expanding space, drifting quietly through the darkness. For many decades, astronomers assumed that this expansion would gradually slow down. Gravity, after all, pulls matter together. The combined gravitational attraction of all the galaxies in the universe should act as a cosmic brake, gradually reducing the rate of expansion over time. That expectation seemed reasonable. But the universe had another surprise waiting. During the late 1990s, two independent teams of astronomers set out to measure the expansion history of the universe using distant stellar explosions known as Type 1a supernovae. These supernovae occur when certain white dwarf stars accumulate too much mass and explode with nearly uniform brightness. Because their intrinsic brightness is well understood, astronomers can use them as cosmic distance markers. By comparing how bright these supernovae appear from Earth with how far away they are, researchers can estimate the expansion rate of the universe at different points in cosmic history. The teams studying these supernovae were led by Saul Perlmutter, Brian Schmidt, and Adam Rees. Their observations revealed something astonishing. The expansion of the universe was not slowing down. It was speeding up. Galaxies were drifting apart faster and faster over time, as though some invisible influence were pushing space outward. This discovery introduced a new concept into cosmology: dark energy. The term dark energy was popularized by the cosmologist Michael Turner to describe the mysterious force or property of space responsible for accelerating cosmic expansion. Unlike ordinary matter or radiation, dark energy does not appear to clump together into structures. Instead, it seems to be spread uniformly throughout space itself. Its exact nature remains one of the greatest open questions in modern physics. Some theories suggest that dark energy may be related to the cosmological constant originally introduced by Einstein. Others propose that it arises from the energy of the quantum vacuum or from fields that permeate space-time. Whatever its origin, the effect is clear. The universe is expanding at an accelerating pace. This acceleration has an important consequence for the long-term structure of the cosmos. As galaxies move farther apart, their interactions become increasingly rare. Over immense periods of time, many galaxies will drift beyond the observable horizon of others, carried away by the expanding fabric of space. The cosmic landscape gradually becomes more isolated. Clusters of galaxies remain bound together by gravity, forming local islands of matter. But beyond those clusters, the universe grows emptier and quieter as the distances between structures increase. The expansion of space therefore acts as a kind of cosmic calming mechanism. In the early universe, matter was packed closely together, and interactions between particles were constant. Over billions of years, expansion stretched those dense conditions into a far more spacious environment. Galaxies formed, clusters assembled, and vast regions of emptiness appeared between them. As the universe continues to expand, these separations will only grow larger. The cosmos will become increasingly quiet. Yet even within this expanding universe, information still travels. Light continues to cross enormous distances, carrying signals from stars, galaxies, and distant cosmic events. Across the growing calm of the cosmos, the universe still communicates. It simply does so in a language very different from sound. Silence, in the ordinary human sense, usually means an absence of sound. But the universe is not truly silent. It simply communicates in a very different language. On Earth, sound travels through air as tiny compressions and rarefactions of molecules. These pressure waves move through matter by pushing neighboring particles, creating the familiar vibrations that eventually reach human ears. Space, however, contains almost no particles. Without a dense medium of molecules, sound waves have nothing to push against. Vibrations cannot propagate through the vacuum between stars in the same way they travel through air or water, and yet the universe is constantly sending signals across those empty distances. Those signals arrive in the form of light. Light belongs to a broader category of phenomena known as electromagnetic radiation. Unlike sound, electromagnetic radiation does not require a material medium to travel. Instead, it moves through space as oscillations of electric and magnetic fields that sustain each other as they propagate forward. This remarkable property allows light to cross the vacuum of space without losing its ability to carry information. The scientific explanation for this behaviour emerged during the 19th century through the work of the Scottish physicist James Clerk Maxwell. Maxwell studied electricity and magnetism, two phenomena that had previously been investigated separately by scientists such as Michael Faraday and André-Marie Ampère. Through careful mathematical analysis, Maxwell discovered that electric and magnetic fields are deeply connected. A changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. These two fields can reinforce one another in a self-propagating pattern that travels through space. Maxwell realized that such oscillations would move at a specific speed determined by the electrical and magnetic properties of space itself. When he calculated that speed, the result matched the measured speed of light. From this insight came a profound conclusion. Light itself is an electromagnetic wave. This realization unified several branches of physics into a single framework now known as classical electromagnetism. It also revealed why light can travel across the vacuum of space even when sound cannot. Sound requires matter. Light requires only fields. Once Maxwell's theory became widely accepted, scientists began to understand that visible light represents only a small portion of a much broader electromagnetic spectrum. Different forms of radiation vary in wavelength and frequency, yet all obey the same underlying principles described by Maxwell's equations. Radio waves occupy the longest wavelengths, microwaves follow next, then infrared radiation. Visible light lies roughly in the middle of the spectrum, representing the narrow band that human eyes evolved to detect. Beyond visible light come ultraviolet radiation, X-rays, and finally gamma rays, which carry enormous energy in extremely short wavelengths. Each region of the spectrum reveals different aspects of the universe. Some cosmic phenomena emit primarily radio waves, while others shine most strongly in infrared or X-rays. By studying multiple wavelengths of electromagnetic radiation, astronomers can piece together a far richer picture of cosmic activity. The sky, when viewed across the full electromagnetic spectrum, becomes far more dynamic than the quiet darkness seen with human eyes alone. A key figure in the early development of radio astronomy was the American engineer and radio enthusiast Grote Reber. During the 1930s, Reber built the first dedicated radio telescope in his backyard in Wheaton, Illinois. Using a large metal dish designed to collect radio waves from the sky, he began systematically mapping radio emissions from the Milky Way. His observations reveal that the galaxy emits radio signals even in regions where visible light appears faint or absent. These early discoveries opened an entirely new window onto the universe. Over time, radio astronomy expanded dramatically, allowing scientists to detect pulsars, study interstellar gas clouds, and observe distant galaxies that would otherwise remain hidden. Today, radio observatories operate on a scale that Robert could scarcely have imagined. One of the most remarkable facilities is the Atacama Large Millimeter Array, located high in the Atacama Desert of northern Chile. This array consists of dozens of precisely synchronized radio antennas spread across the desert plateau. Together they function as a single enormous telescope capable of detecting extremely faint radio signals from distant cosmic structures. These observations reveal cold clouds of gas where stars are forming, swirling disks of material around young stars, and even the faint afterglow of radiation left over from the earliest moments of cosmic history. Another revolutionary observatory is the James Webb Space Telescope. Launched into deep space beyond the orbit of the Moon, the James Webb Space Telescope observes the universe primarily in infrared wavelengths. Infrared light is particularly useful for studying distant galaxies and star-forming regions because it can pass through clouds of dust that block visible light. By detecting faint infrared signals that have travelled across billions of years of cosmic expansion, the telescope allows astronomers to glimpse galaxies that formed when the universe was still very young. Even objects that appear dark to human eyes can glow brightly in infrared radiation. Across the electromagnetic spectrum, the universe is constantly broadcasting information. Stars emit light produced by nuclear fusion in their cores. Galaxies shine with the combined glow of billions of stars. Black holes generate powerful radiation as matter spirals inward through hot accretion disks. Supernova explosions release bursts of electromagnetic energy, visible across vast cosmic distances. All of these signals move through space as electromagnetic waves. Even though space itself contains almost no air, these waves travel effortlessly across the vacuum. Light leaving a distant galaxy can cross billions of light years before reaching a telescope on Earth. That light carries a record of the conditions present when it was first emitted. By analyzing its color, intensity, and spectral features, astronomers can determine the temperature, composition, motion, and distance of the objects that produced it. In this way, light becomes the primary messenger of the universe. Every star in the night sky is sending a steady stream of photons across space. Every distant galaxy is quietly broadcasting its presence through electromagnetic radiation. The signals are everywhere, but they do not arrive as sound. They arrive as light. This difference explains why the universe appears silent when imagined through human senses. Our ears evolved to detect pressure waves in air, not oscillating electric and magnetic fields travelling through the vacuum of space. The cosmos may not roar or rumble in the traditional sense, yet it is far from inactive. Instead, it communicates continuously, through patterns of electromagnetic radiation that travel immense distances without the need for a medium. Through telescopes sensitive to different wavelengths, astronomers have learned to listen to this silent conversation of light. The universe speaks, just not in sound, and when those signals reveal the most energetic events in existence, they show that beneath the calm appearance of the cosmos lie extraordinary bursts of activity unfolding across unimaginable distances. The universe may appear calm when viewed from a distance, but beneath that quiet surface, extraordinary events unfold constantly. Across the vastness of space, stars explode, neutron stars collide, and magnetic fields twist with such intensity that they briefly outshine entire galaxies. These events release staggering amounts of energy, yet they remain almost completely unnoticed on the scale of the universe as a whole. The reason is simple: distance. When violent cosmic events occur millions or billions of light years away from one another, their immense energies disperse into the surrounding void long before they can interact with anything else. The result is a universe that looks serene from afar, even while astonishing phenomena erupt within it. One of the most dramatic events in astrophysics is the death of a massive star in a supernova explosion. Stars spend most of their lives quietly fusing hydrogen into helium deep within their cores. This process generates energy that pushes outward against the inward pull of gravity. For millions or billions of years, that balance keeps the star stable. But eventually the balance fails. When a massive star exhausts the nuclear fuel in its core, gravity takes over. The star's inner layers collapse inward with incredible speed, compressing matter to densities so extreme that atomic nuclei are forced tightly together. The collapse halts abruptly when the core becomes a neutron star, a compact object so dense that a teaspoon of its material would weigh billions of tons on Earth. That sudden halt produces a violent rebound. The outer layers of the star are blasted outward in an explosion known as a core collapse supernova. For a brief period, the exploding star can shine as brightly as an entire galaxy. Yet despite the energy released, these events are separated by immense cosmic distances. The nearest supernova visible to the naked eye in recent centuries occurred in the year 1987, when a star exploded in the Large Magellanic Cloud, a small neighbouring galaxy. Even that relatively nearby event took about 160,000 years for its light to reach Earth. The universe operates on timescales and distances so large that even the most spectacular explosions unfold quietly across the cosmic landscape. Some events are even more energetic. Among the most powerful phenomena ever observed are gamma-ray bursts, brief flashes of extremely high-energy radiation that can release more energy in a few seconds than the Sun will produce in its entire lifetime. For decades, these mysterious bursts puzzled astronomers. They were first detected in the 1960s by satellites designed to monitor nuclear explosions on Earth. Instead of human activity, the detectors recorded bursts of gamma radiation arriving from distant parts of the sky. Understanding these events required decades of observation and theoretical work. One of the leading contributors to gamma-ray burst theory is the astrophysicist Stan Woosley. His research helped develop models in which certain gamma-ray bursts occur when extremely massive stars collapse into black holes. In this scenario, the collapsing star forms a rapidly rotating disk of matter around the newly formed black hole. Jets of high-energy particles are launched outward along the star's rotational axis at speeds approaching that of light. When those jets break through the outer layers of the star and blast into space, they produce intense beams of gamma radiation detectable across enormous distances. Because the jets are highly focused, gamma-ray bursts are visible only when one of the beams happens to point toward Earth. For a few seconds, the burst becomes one of the brightest events in the observable universe. Then it fades. Another remarkable source of cosmic violence arises when neutron stars collide. Neutron stars are already extreme objects. Formed from the collapsed cores of massive stars, they contain more mass than the Sun compressed into a sphere roughly the size of a city. Their gravitational fields are immense. When two neutron stars orbit each other in a binary system, they gradually spiral inward as they lose energy through the emission of gravitational waves. These waves are subtle ripples in space-time itself, predicted by Albert Einstein's theory of general relativity. As the stars draw closer together, their orbital motion accelerates. Eventually, they collide in a violent merger that produces a burst of gravitational waves and electromagnetic radiation. The collision can also forge heavy elements such as gold and platinum through a process known as rapid neutron capture. For many years, gravitational waves remained purely theoretical. But in the early 21st century, scientists built instruments capable of detecting these incredibly subtle distortions of space-time. One of the most important facilities for this work is the Laser Interferometer Gravitational Wave Observatory, widely known by its acronym. The Laser Interferometer Gravitational Wave Observatory consists of large detectors located in the United States that measure tiny changes in distance caused by passing gravitational waves. The observatory was developed through decades of research led by scientists including Rainer Weiss, Kip Thorne, and Ronald Drever. In the year 2015, the observatory made history. It detected the first confirmed gravitational waves produced by the merger of two black holes more than a billion light-years away. The signal lasted only a fraction of a second, yet it revealed an event of enormous energy occurring deep within the cosmos. A few years later, another detection captured the gravitational waves produced by merging neutron stars. For the first time, astronomers were able to observe both gravitational waves and electromagnetic radiation from the same cosmic event. Telescopes across the world quickly turned toward the region of the sky where the merger occurred. They watched as the collision produced a glowing cloud of expanding debris. Even these astonishing events, however, remain separated by staggering distances. Between one violent event and the next lies an ocean of empty space. The universe contains enormous energy, but it is distributed across volumes so vast that most of it never interacts. Another example of extreme astrophysical phenomena involves objects known as magnetars. Magnetars are a rare type of neutron star possessing magnetic fields of extraordinary strength. These fields are so powerful that they can distort the very structure of atoms near the star's surface. Theoretical work by astrophysicists Robert Duncan and Christopher Thompson helped explain how such intense magnetic fields might form. According to their models, certain rapidly rotating neutron stars can amplify their magnetic fields through a process similar to a dynamo, creating fields trillions of times stronger than Earth's magnetic field. When the magnetic field lines within a magnetar shift or fracture, they can release sudden bursts of high-energy radiation. These events are sometimes called starquakes. For a brief moment, a magnetar flare can release as much energy as the Sun emits in hundreds of thousands of years. Yet even these spectacular outbursts are swallowed by cosmic distance. A magnetar flare occurring in a distant galaxy might travel millions of years before its radiation reaches Earth. By the time the signal arrives, the event itself is long over. What remains is a faint whisper of a once violent moment. This pattern repeats throughout the cosmos. Stars explode, neutron stars collide, magnetars flare, black holes consume matter and launch jets of radiation across intergalactic space. Each event represents an extraordinary release of energy. But because the universe is so vast, these events occur far apart from one another. They rarely overlap, rarely interact, and rarely disturb the calm appearance of the cosmic landscape. Seen from afar, the universe appears tranquil, not because nothing happens, but because everything happens so far away. Violence exists throughout the cosmos, yet it is diluted across unimaginable distances. The enormous spaces between galaxies and stars act as buffers, spreading energy so thinly that most of the universe remains quiet and dark. This immense quietness raises another question. If powerful astrophysical events occur across the universe, and if light and other signals travel vast distances through space, then perhaps other forms of signals could also exist. Signals created not by stars or black holes, but by intelligent beings. And yet, despite decades of listening, the cosmos remains strangely silent on that front as well. For much of human history, the night sky appeared quiet, simply because the universe is vast. But during the 20th century, a new question began to emerge. If the universe contains hundreds of billions of galaxies, and each galaxy contains hundreds of billions of stars, then somewhere among those countless worlds there might be other civilizations capable of building technology. Civilizations capable of transmitting signals, civilizations capable of communicating across space. Yet when astronomers listen carefully to the sky, they hear nothing that clearly comes from intelligent life. This puzzle is often summarized in a simple question, first asked by the physicist Enrico Fermi. "Where is everybody?" Fermi reportedly raised this question during a casual lunchtime conversation in the early 1950s at Los Alamos National Laboratory. The discussion began with speculation about extraterrestrial travel and the possibility of advanced civilization spreading across the galaxy. But Fermi pointed out something curious. If intelligent civilizations were common in the Milky Way, then some of them might have had millions of years to expand, explore, or communicate. Even at modest speeds, a civilization capable of interstellar travel could theoretically spread throughout the galaxy over cosmic timescales. And yet, the sky remains quiet. No obvious spacecraft, no unmistakable signals, no clear signs of vast technological structures surrounding distant stars. The apparent contradiction between the large number of potentially habitable worlds and the lack of detected civilizations became known as the Fermi question, or sometimes the Fermi paradox. The paradox arises from a simple comparison. The universe seems enormous and full of stars, but evidence of extraterrestrial intelligence appears absent. To explore this problem more carefully, astronomers and scientists developed ways to think about the probability of intelligent life emerging elsewhere. One of the most well-known approaches is the Drake equation. The Drake equation was introduced in 1961 by the American astronomer Frank Drake during a scientific meeting focused on the search for extraterrestrial intelligence. Rather than attempting to produce a single precise number, the equation provides a framework for thinking about the many factors that might influence the existence of technological civilizations. It considers several ingredients: the rate at which stars form in a galaxy, the fraction of those stars that possess planetary systems, the number of planets that might support life, the fraction of those planets where life actually arises, the fraction of life-bearing worlds where intelligent species evolve, the fraction of those species that develop technology capable of sending detectable signals, and finally, the length of time those civilizations continue transmitting such signals. When these factors are multiplied together, the result estimates how many technological civilizations might exist within a galaxy at any given time. The Drake equation does not provide a definitive answer, because many of its variables remain uncertain. But it highlights an important idea. The silence of the cosmos may not necessarily mean that intelligent life is rare. Instead, it may reflect the difficulty of detecting civilizations across the immense distances of space. Still, the question remains: if intelligent life has emerged elsewhere, why have no signals clearly appeared? Several explanations have been proposed. One possibility involves a concept known as the Great Filter. The Great Filter idea was developed by the economist and philosopher Robin Hanson. It suggests that somewhere Along the long chain of steps required for intelligent life to develop, there may be an extremely difficult barrier. This barrier might occur early in the process, perhaps making the origin of life itself incredibly rare. Alternatively, the filter might occur later, preventing civilizations from surviving long enough to spread across the galaxy. If such a filter exists, it could explain why the universe appears quiet. Perhaps very few civilizations ever reach the stage where they can communicate across interstellar distances. Another intriguing idea is known as the zoo hypothesis. This concept was proposed by the scientist John Ball, who suggested that advanced civilizations might deliberately avoid contacting developing worlds such as Earth. According to this idea, Earth could be treated somewhat like a protected wildlife preserve, a kind of cosmic zoo. In this scenario, advanced civilizations might observe emerging societies without interfering with their development. They might even hide their presence to avoid disrupting the natural evolution of young civilizations. While this idea remains speculative, it highlights how little is truly known about the behavior of hypothetical extraterrestrial cultures. Even if other civilizations exist, their priorities, technologies, and communication methods might differ greatly from human expectations. Meanwhile, scientists on Earth have continued searching for signals that could indicate intelligent activity. One of the most prominent organizations involved in this effort is the SETI Institute, whose name stands for the Search for Extraterrestrial Intelligence. Researchers associated with the SETI Institute use radio telescopes to scan the sky for unusual patterns in radio waves. These observations look for signals that might stand out from natural cosmic emissions. For example, a narrow-frequency transmission that repeats in a structured pattern could potentially indicate an artificial source. So far, despite decades of observation, no confirmed technological signal has been detected. The sky remains quiet. This does not necessarily mean that signals are absent. It may simply reflect the enormous challenge of searching across the vast electromagnetic spectrum and the immense distances separating stars. The physicist Ronald Bracewell explored another aspect of this problem through the concept of interstellar communication networks. Bracewell suggested that advanced civilizations might send automated probes or communication relays across the galaxy. These devices could act as messengers, quietly transmitting information between star systems over long periods of time. If such probes exist, they might operate silently, waiting for the right conditions to communicate with emerging civilizations. But detecting them would be extraordinarily difficult. The distances between stars stretch across trillions upon trillions of kilometers. Even signals traveling at the speed of light require years, decades, or centuries to cross these distances. Communication across such scales becomes a slow and delicate process. Messages sent between stars might resemble conversations conducted across vast stretches of time rather than across moments. This cosmic scale introduces another complication. Civilizations may simply miss each other. One society might develop advanced technology, transmit signals for a few thousand years, and then fade away. Another civilization might arise millions of years later in a distant region of the galaxy. Their signals would never overlap. In a universe billions of years old, the lifetimes of technological societies may be brief flashes in comparison. If those flashes rarely occur at the same time and within the same region of space, the sky could remain quiet even if many civilizations have existed at different moments in cosmic history. The silence might not mean emptiness. It might simply mean separation. Across the vast structure of the cosmos, signals travel. Slowly, distances remain immense, and civilizations may appear and disappear across millions of years. From Earth's perspective, the night sky still seems silent. Yet beneath that silence lies a deeper question about how information travels across the universe and how astronomers continue searching for signals of all kinds, not only from intelligent life, but from the natural processes of the cosmos itself. Long before telescopes were built to observe radio waves from distant galaxies, the discovery of cosmic radio signals began almost by accident. During the early 1930s, an engineer named Karl Jansky was working for Bell Telephone Laboratories in the United States. His task was not originally related to astronomy at all. Instead, he was investigating sources of interference that affected transatlantic radio communications. To study the problem, Jansky constructed a large rotating antenna designed to detect faint radio signals from across the sky. The unusual device looked somewhat like a carousel made of metal pipes and wires. When he began analyzing the signals received by his antenna, Jansky noticed something curious. Among the various sources of interference, one signal appeared to repeat in a steady pattern. It rose and fell in strength once every 23 hours and 56 minutes. That interval matched the rotation of Earth relative to the stars rather than the Sun. The signal, it seemed, was coming from space. After careful investigation, Jansky traced the source of the radio emission to the direction of the constellation Sagittarius, which lies toward the dense central region of the Milky Way galaxy. This observation marked the first detection of radio waves originating from beyond Earth. Without intending to, Jansky had opened an entirely new window onto the universe. His discovery revealed that the sky was not silent in the radio portion of the electromagnetic spectrum. Invisible signals were constantly arriving from distant cosmic sources, carrying information about energetic processes occurring far beyond the solar system. Although Jansky's work was groundbreaking, radio astronomy did not immediately become a major field of research. Much of the early development came from the determination of a single enthusiast. Grote Reber, an American amateur radio operator, was fascinated by Jansky's discovery. Determined to explore these mysterious signals further, Reber decided to build his own radio telescope. In the late 1930s, he constructed a large parabolic dish in his backyard in Wheaton, Illinois. The telescope measured roughly 30 feet across and was designed to collect radio waves from the sky and focus them onto a receiver at its center. Night after night, Reber pointed his telescope toward different regions of the heavens, carefully recording the radio signals he detected. Through years of patient observation, he created the first detailed radio maps of the Milky Way. Reber's work demonstrated that radio emissions were widespread across the galaxy. Regions filled with gas, dust, and energetic particles produced radio signals even where visible light was faint or absent. His dedication helped transform radio astronomy from a curious observation into a serious scientific discipline. As technology advanced in the decades that followed, radio telescopes grew larger and more sensitive. Astronomers began discovering new and unexpected phenomena hidden within radio signals from space. One of the most remarkable discoveries occurred in the late 1960s. At the University of Cambridge, a graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope designed to study distant radio sources. While examining the recordings, she noticed a strange pattern of repeating pulses. The signals arrived with extraordinary regularity. At first, the pattern seemed almost artificial. Some researchers jokingly referred to the source as little green men, imagining that the pulses might come from an extraterrestrial transmitter. But further investigation revealed a natural explanation. The signals were coming from an object now known as a pulsar. Pulsars are rapidly rotating neutron stars formed in the aftermath of supernova explosions. These dense stellar remnants possess extremely strong magnetic fields that channel beams of electromagnetic radiation outward from their magnetic poles. As the neutron star spins, those beams sweep through space like the rotating light of a lighthouse. If one of those beams crosses Earth, astronomers detect a brief pulse of radio waves each time the star rotates. Some pulses spin several times per second. Others rotate more slowly, but all exhibit remarkable precision, with pulse intervals so regular that they rival the accuracy of atomic clocks. The discovery of pulsars, credited to Jocelyn Bell Burnell and her research supervisor Anthony Hewish, revealed another layer of cosmic activity hidden within radio signals. Objects invisible to ordinary telescopes were broadcasting rhythmic patterns across the galaxy. As radio astronomy continued to develop, scientists learned that many powerful cosmic phenomena emit strong radio waves. Distant galaxies containing supermassive black holes can produce enormous jets of energetic particles that extend far beyond the galaxy itself. These jets emit intense radio radiation as charged particles spiral through magnetic fields at near light speed. Even regions where new stars are forming can generate radio signals. Clouds of cold hydrogen gas scattered across the galaxy emit faint radio emissions at characteristic wavelengths. By mapping these signals, astronomers can trace the structure and motion of gas within the Milky Way. Radio observations therefore reveal a dynamic universe filled with processes that remain invisible in ordinary light. Detecting these signals requires extremely sensitive instruments. Radio waves arriving from distant galaxies are often unimaginably faint by the time they reach Earth. To capture them, astronomers build large antenna arrays that collect radio energy across wide areas and combine the signals to simulate a much larger telescope. One of the most ambitious projects currently underway is the Square Kilometre Array. The Square Kilometre Array will consist of thousands of radio antennas spread across remote regions of Australia and South Africa. When fully operational, these antennas will work together as a single integrated observatory with a total collecting area approaching 1 square kilometre. This enormous sensitivity will allow astronomers to detect radio signals from extremely distant galaxies and probe some of the earliest structures formed in the universe. The observatory will also help search for faint signals associated with cosmic hydrogen gas, map the large-scale structure of the cosmos, and investigate the environments surrounding supermassive black holes. Through instruments like these, astronomers effectively listen to the universe, not with ears, but with radio receivers. Instead of sound waves traveling through air, radio telescopes capture oscillations of electromagnetic fields arriving from across space. The signals are then converted into data that can be analyzed, mapped, and sometimes even translated into audible tones. In this sense, radio astronomy transforms invisible cosmic signals into something that can be interpreted as a kind of listening. The universe may not produce sound in the traditional sense, yet it continuously broadcasts radio signals that reveal its hidden activity. Pulsars pulse, galaxies emit jets, clouds of hydrogen glow faintly in radio frequencies, and distant cosmic structures send whispers of energy across billions of years of space and time. Through radio telescopes, astronomers have learned that the quiet sky is anything but empty. Instead, it is filled with faint messages carried by electromagnetic waves. Among those signals lies one of the most important clues about the earliest moments of cosmic history, a faint glow that fills all of space, a relic from a time when the universe itself was far younger and far more energetic than it is today. Even after exploring exploding stars, distant galaxies, and mysterious radio pulses, there remains another signal filling the entire universe. It is faint, it is ancient, and it is everywhere. This signal is known as the cosmic microwave background radiation, often described as the oldest light that can still be observed in the universe. It does not come from a single star or galaxy. Instead, it fills all of space almost uniformly, arriving from every direction in the sky. For astronomers, it represents something extraordinary, a relic from the earliest visible moment in cosmic history. To understand why this radiation exists, it helps to imagine the universe shortly after the Big Bang. In its earlier stages, the universe was incredibly hot and dense. Matter and radiation were mixed together in a glowing plasma where electrons, protons, and photons constantly interacted with one another. Light could not travel freely. Every photon quickly collided with charged particles scattering in random directions. The universe was therefore opaque, somewhat like the interior of a dense fog. But as the universe expanded, it gradually cooled. Roughly 380,000 years after the Big Bang, the temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. This process is known as recombination, although it was actually the first time those particles had combined in this way. Once neutral atoms formed, photons were no longer scattered constantly by free electrons. Light could finally travel freely across space. The radiation released at that moment has been traveling through the universe ever since. Over billions of years, the expansion of the universe stretched the wavelengths of that ancient light, gradually shifting it into the microwave portion of the electromagnetic spectrum. What began as intensely energetic radiation has cooled into a faint glow detectable only with sensitive instruments. Yet even in its weakened form, it remains one of the most important signals in cosmology. The existence of this background radiation was first detected in the 1960s by radio astronomers Arno Penzias and Robert Wilson. While working with a large radio antenna in New Jersey, they encountered a persistent source of microwave noise that appeared to come from every direction in the sky. At first, they suspected equipment problems. They carefully inspected their instruments, cleaned the antenna, and even removed pigeons nesting inside the structure. But the signal remained. Eventually they realized that what they were detecting was not interference at all. It was the faint afterglow of the early universe. The discovery provided powerful confirmation for Big Bang cosmology, which had predicted that such relic radiation should exist. Once astronomers recognized the significance of this signal, they began designing experiments to study it in greater detail. Several space missions were launched to map the cosmic microwave background with increasing precision. One of the earliest of these missions was the Cosmic Background Explorer satellite, often called COBE. Launched in the late 1980s, COBE measured the temperature of the background radiation across the sky. The results confirmed that the radiation has an almost perfectly uniform temperature. Across the entire observable universe, the background glow measures only a few degrees above absolute zero. This remarkable uniformity revealed that the early universe was astonishingly smooth on large scales. Yet the most important discovery from the COBE mission involved tiny variations within that smooth background. The satellite detected minute fluctuations in temperature, differences so small they amounted to only a few millionths of a degree. These tiny irregularities were not measurement errors. They were real features of the early universe. The cosmologist George Smoot, who played a leading role in analyzing the COBE data, famously described these fluctuations as the seeds of cosmic structure. Those tiny variations represented regions where matter was slightly more concentrated than average. Over billions of years, gravity amplified those small differences. Regions with slightly more matter attracted additional material, gradually forming galaxies, clusters of galaxies, and the large-scale cosmic web observed today. In other words, the immense structures that fill the universe today can be traced back to faint ripples in the ancient background radiation. Later missions expanded upon the discoveries of COBE. The Wilkinson Microwave Anisotropy Probe, known as WMAP, was launched in the early 2000s to produce a more detailed map of the cosmic microwave background. Its observations revealed the structure of those temperature fluctuations with far greater precision. WMAP helped refine estimates of the universe's age, composition, and geometry. By studying the subtle patterns within the background radiation, cosmologists were able to determine that the universe is approximately 13.8 billion years old. The mission also provided strong evidence that ordinary matter makes up only a small fraction of the cosmos, while dark matter and dark energy dominate the universe on large scales. A later mission, the Planck satellite operated by the European Space Agency, extended this work even further. Launched in the early 2010s, Planck measured the cosmic microwave background with extraordinary sensitivity. Its maps revealed intricate patterns of fluctuations across the sky, offering the most detailed snapshot ever obtained of the early universe. These patterns encode information about the conditions that existed shortly after the Big Bang. By analyzing them carefully, scientists can reconstruct aspects of the universe's early evolution, including how matter was distributed and how the first structures began to form. In this sense, the cosmic microwave background acts as a kind of photograph, not of stars or galaxies, but of the universe itself when it was still very young. The light detected today began its journey when the cosmos was only a few 100,000 years old, long before the first stars ignited. For billions of years it has travelled through expanding space, carrying with it a record of the early universe. Every direction in the sky reveals the same ancient glow. The universe may appear quiet and empty, yet it still contains this faint echo of its own creation. This signal is extraordinarily subtle, but it tells a profound story. It reveals that even the quietest regions of space carry traces of events that occurred billions of years ago. The universe is filled with information, preserved in the radiation that continues to cross cosmic distances. The silence of the cosmos is therefore not an absence of history. It is a stillness layered over an ancient record. And as the universe continues to evolve, deeper physical processes will shape its future, gradually transforming the energetic cosmos of the past into an ever more spacious and tranquil expanse. The quietness of the universe is not only a matter of distance, it is also a matter of time. Over billions of years, the cosmos has been gradually changing in a direction that physicists describe using a concept known as entropy. This idea emerged during the 19th century as scientists began studying heat, energy, and the behavior of physical systems. One of the key figures in developing this concept was the Austrian physicist Ludwig Boltzmann. Boltzmann sought to understand why certain physical processes seem to move in only one direction. Heat flows from hotter objects to colder ones. Gas spreads out to fill available space. Energy becomes more evenly distributed over time. These everyday observations led to the formulation of the second law of thermodynamics. In simple terms, the law states that the total entropy of an isolated system tends to increase. Entropy can be understood as a measure of disorder, or more precisely, a measure of how many microscopic arrangements are possible for a given physical state. Systems naturally evolve toward configurations that can be realized in many different ways rather than toward highly ordered arrangements that require very specific conditions. Boltzmann expressed this relationship in a concise statement, connecting entropy to the number of microscopic configurations available to a system. The principle can be summarized as entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of possible microscopic states. Although this equation was originally developed to describe gases and heat engines, its implications reach far beyond steam engines and laboratory experiments. The same thermodynamic principles apply to stars, galaxies, and the universe itself. Cosmic systems also obey the laws of thermodynamics. Stars provide a clear example. A star forms when gravity pulls together a large cloud of gas, primarily hydrogen. As the cloud collapses, gravitational energy converts into heat, raising the temperature at the center of the forming star. Eventually, the temperature becomes high enough for nuclear fusion to begin. Inside the core of a star, hydrogen nuclei combine to form helium. This fusion process releases enormous amounts of energy, which slowly travels outward through the star and eventually escapes as radiation. The light from stars spreads across space, carrying energy away from the dense hot core into the colder surroundings of the universe. In thermodynamic terms, this process increases entropy. Energy begins in a highly concentrated state inside the stellar core. Over time, it disperses outward as radiation traveling through space in all directions. Stars therefore act as engines that gradually spread energy across the cosmos. But even these engines do not last forever. Stars consume their nuclear fuel slowly over millions or billions of years. As the fuel becomes depleted, the internal balance between gravity and radiation pressure begins to change. Some stars expand into red giants, others collapse into compact remnants such as white dwarfs, neutron stars, or black holes. In each case, the long-term trend is the same. Energy becomes more widely distributed, heat flows outward, entropy increases. On cosmic timescales, this gradual redistribution of energy contributes to the calming of the universe. Early in cosmic history, matter was densely packed, and interactions between particles were frequent. As the universe expanded and cooled, matter spread into galaxies and clusters, while radiation traveled outward across increasingly vast regions of space. The universe became more spacious and more thermodynamically relaxed. The physicist Roger Penrose has explored these ideas in great depth while studying the thermodynamics of the cosmos. Penrose pointed out that the early universe, despite its high temperature and density, actually possessed very low gravitational entropy. Matter was distributed extremely smoothly across space, with very little large-scale structure. From a thermodynamic perspective, this smoothness represented a highly ordered configuration. As the universe evolved, gravity began amplifying small irregularities in the distribution of matter. Regions that were slightly denser attracted more material, eventually forming stars, galaxies, and clusters. These structures increased the overall entropy of the universe by creating complex gravitational systems capable of redistributing energy. Black holes play an especially important role in this process. According to theoretical work by physicists such as Jacob Bekenstein and Stephen Hawking, black holes possess enormous entropy. Their event horizons store vast amounts of information about the matter and energy that have fallen into them. In fact, black holes may represent some of the highest entropy objects in the universe. As stars collapse and galaxies evolve, more matter eventually becomes locked inside black holes. Over extremely long timescales, these objects dominate the thermodynamic landscape of the cosmos, yet even black holes do not remain forever. Quantum effects near their event horizons allow them to slowly radiate energy through a process known as Hawking radiation. Over unimaginable stretches of time, black holes themselves gradually evaporate. The universe therefore continues moving towards states where energy becomes more evenly spread. Hot regions cool, dense structures dissipate, radiation drifts across ever larger expanses of space. Entropy steadily increases. This trend helps explain why the universe appears calm on large scales, as the energy spreads outward and matter becomes more widely separated. Interactions between systems become less frequent. Violent events such as supernova explosions or neutron star collisions still occur, but they become isolated moments rather than constant disturbances. The cosmic environment grows quieter, not because activity stops entirely, but because energy disperses across such vast volumes of space. The same thermodynamic principles that govern heat, flowing from a warm cup of tea into a cool room, also shape the evolution of galaxies and stars across billions of years. Energy spreads. Order gives way to more probable configurations, and the universe gradually approaches states of greater thermodynamic balance. From this perspective, cosmic quietness is not mysterious at all. It is a natural consequence of the laws of physics. The second law of thermodynamics quietly guides the evolution of the universe, encouraging energy to spread outward and systems to move toward equilibrium. In the distant future, this process will continue to shape the fate of the cosmos. Stars will eventually exhaust their fuel, galaxies will grow dimmer, the universe will expand ever further, leaving cosmic structures more widely separated than ever before. What began as an intensely energetic beginning will slowly evolve into a far calmer cosmic landscape. A universe where energy has spread thinly across enormous distances. A universe where quietness becomes the natural state. And as physicists explore the long-term future of the cosmos, they attempt to understand exactly how this slow thermodynamic journey might unfold across unimaginable stretches of time. The quietness of the universe observed today is not merely a temporary feature of the present cosmic era. According to modern astrophysics, it is part of a much larger story unfolding over unimaginably long stretches of time. The cosmos is slowly evolving toward an even calmer future. Stars are currently the primary engines of visible activity in the universe. They shine through nuclear fusion, transforming hydrogen into helium and releasing enormous amounts of energy as radiation. This process illuminates galaxies, powers planetary systems, and produces many of the elements that make planets and life possible. But stars rely on fuel, and that fuel is finite. The gas that forms stars is mainly hydrogen floating in vast interstellar clouds within galaxies. Over billions of years, gravity gathers portions of this gas into dense regions where new stars ignite. Each generation of star formation consumes part of this cosmic reservoir. Gradually the supply diminishes. Astrophysicists studying the long-term evolution of the universe have examined what will happen when this process continues for far longer than the current age of the cosmos. Two researchers who explored these ideas in depth are Fred Adams and Gregory Laughlin. Their work focuses on what they describe as the far future of cosmic evolution. Adams and Laughlin analyzed how star formation, stellar lifetimes, and gravitational interactions shape the destiny of galaxies over immense timescales. Their research suggests that the present era of active star formation represents only a temporary phase in cosmic history. Eventually, galaxies will begin to run out of the raw material needed to create new stars. large clouds of hydrogen gas will either be consumed by star formation or expelled from galaxies through energetic processes such as supernova explosions and galactic winds. Without sufficient gas, the birth of new stars will slow dramatically. The universe will gradually grow dimmer. This transition is already beginning. Astronomical observations show that the rate of star formation across the universe peaked several billion years ago and has been declining ever since. Galaxies still produce new stars, but the overall pace is slower than it once was. Given enough time, star formation will become extremely rare. The stars that already exist will continue shining for long periods, especially the smallest ones. Red dwarf stars, which contain far less mass than the Sun, burn their nuclear fuel slowly and efficiently. Some of them may remain luminous for trillions of years, yet even these long-lived stars will eventually fade. Once their hydrogen fuel is exhausted, they will cool and dim, becoming dense stellar remnants known as white dwarfs. Over vast periods of time, these remnants will continue cooling until they become extremely cold objects, sometimes called black dwarfs. By that stage, galaxies will contain mostly stellar remnants rather than shining stars. The cosmic landscape will grow darker. Meanwhile, another type of object will become increasingly important in shaping the future universe: black holes. Black holes already exist at the centers of most large galaxies, including the Milky Way. These supermassive black holes contain millions or billions of times the mass of the Sun and exert enormous gravitational influence on their surroundings. In the distant future, as stars fade and galaxies evolve, black holes may become some of the most dominant objects in the universe. Gravitational interactions between stars will occasionally fling objects out of their host galaxies, leaving behind increasingly sparse stellar populations. Many remaining stars and stellar remnants will eventually spiral toward the central black hole through complex gravitational processes. Over time, black holes may accumulate large amounts of matter, yet even this process will not last forever. Black holes themselves slowly lose energy through Hawking radiation, a quantum effect predicted by physicist Stephen Hawking. This radiation causes black holes to evaporate gradually over incredibly long periods of time. The evaporation of stellar mass black holes would require timescales far beyond the current age of the universe. For the largest supermassive black holes, the process may take time spans so enormous that they're almost impossible to imagine. Eventually, however, even these objects will disappear. Another factor shaping the future quietness of the cosmos is the continued expansion of space itself. The discovery that the universe is expanding at an accelerating rate means that galaxies will drift farther apart as time passes. Regions of space that are currently visible may eventually move beyond the observable horizon, carried away by cosmic expansion. Galaxies will become isolated islands in an ever-growing ocean of emptiness. In the far future, observers within a galaxy may no longer be able to see most of the universe beyond their local cluster. Distant galaxies will recede so quickly that their light will never reach them. From such a perspective, the universe would appear much smaller and quieter than it does today. The night sky would contain fewer visible galaxies. Cosmic structures would become increasingly isolated. These predictions paint a picture of a universe that grows progressively calmer over time. The energetic youth of the cosmos, filled with star formation and galaxy collisions, gradually gives way to a quieter era dominated by aging stars and cooling remnants. Eventually, even those remnants fade, leaving behind a universe where activity becomes rare and energy is dispersed across vast volumes of space. This long-term evolution reflects the same thermodynamic principles discussed earlier. Energy spreads, structures evolve, and the universe slowly approaches states where interactions become less frequent. In that distant future, cosmic quietness will not simply be a matter of distance. It will be a fundamental characteristic of the universe itself. Galaxies will drift apart across expanding space, star formation will decline, and the remaining objects will slowly cool and fade into darkness. Yet within this quiet future lies a deeper perspective. The universe is not merely a physical system evolving according to thermodynamic laws, it is also the environment in which conscious observers have arisen, capable of studying its history and contemplating its destiny. The realization that humanity lives during a relatively active era of cosmic history invites reflection. The present universe, with its shining stars and visible galaxies, may represent only a brief luminous chapter within a far longer and quieter cosmic story. And understanding that story naturally leads to deeper questions about humanity's place within such an immense and slowly evolving universe. The universe may appear quiet, but it has never truly been ignored. Across centuries of observation, human curiosity has steadily grown alongside the realization that the cosmos is far larger and more complex than earlier generations imagined. The night sky, once interpreted through myth and philosophy, gradually became an object of precise scientific investigation. Humanity learned not only to look upward, but to measure. This transformation began with simple instruments and careful observation, yet it eventually grew into a global effort involving powerful telescopes, observatories, and research institutions dedicated to exploring the universe. These tools allow astronomers to study a cosmos that seems calm and distant, revealing subtle signals hidden within that quietness. The stillness of space has become a laboratory. Among the many institutions devoted to this work, the European Southern Observatory represents one of the most ambitious collaborations in modern astronomy. Founded during the 20th century, the organization operates several major observatories in the high deserts of northern Chile. The location was chosen carefully. The Atacama Desert offers some of the clearest skies on Earth. The air is dry, the atmosphere is stable, and far from large cities, there is little artificial light to interfere with observations. These conditions allow telescopes to detect extremely faint signals arriving from distant galaxies and stars. Within this landscape stand enormous instruments designed to collect tiny traces of light that have traveled across cosmic distances. One of the most famous facilities operated by the European Southern Observatory is the Very Large Telescope, a system of powerful telescopes working together on a mountaintop known as Cerro Paranal. These instruments observe the sky with extraordinary sensitivity, allowing astronomers to study planets orbiting distant stars, measure the motion of galaxies, and examine the environments surrounding supermassive black holes. Even faint whispers of light can reveal enormous discoveries. The quietness of space actually makes such measurements possible. Because there are almost no atmosphere or matter between stars, electromagnetic signals can travel vast distances without being scattered or absorbed. When that light finally reaches a telescope, it carries detailed information about the objects that produced it. Every photon becomes a messenger. The ability to interpret these signals depends not only on technology, but also on the work of scientists who carefully analyze the data collected by these instruments. Over time, their efforts have transformed subtle patterns of light into profound insights about the structure of the universe. One astronomer whose work reshaped modern cosmology was Vera Rubin. Rubin dedicated much of her career to studying the rotation of galaxies. Using spectroscopic measurements collected from observatories in the United States, she examined how stars orbit the centers of spiral galaxies. According to classical expectations based on visible matter alone, stars located farther from the center of a galaxy should move more slowly than those closer in, much as planets farther from the Sun orbit more slowly than inner planets. But Rubin's observations revealed something unexpected. Stars far from the galactic center were moving just as quickly as stars closer to the middle. The outer regions of galaxies were rotating far faster than visible matter alone could explain. This discovery provided powerful evidence for the existence of dark matter, an invisible form of matter that exerts gravitational influence yet does not emit or reflect detectable light. Rubin's careful measurements helped establish dark matter as one of the central components of modern cosmology. Her work demonstrated how extremely subtle observations can transform scientific understanding. In many ways, the calmness of the universe makes such discoveries possible. Because cosmic signals travel across enormous distances without constant interference, astronomers can detect incredibly faint variations in light, radio waves, and other forms of radiation. Tiny shifts in wavelength reveal the motion of galaxies. Faint fluctuations in background radiation reveal the structure of the early universe. Minute variations in brightness reveal planets orbiting distant stars. Each of these discoveries relies on the ability to measure signals that would otherwise be lost in a noisier environment. The quietness of space becomes an advantage. If the universe were filled with constant collisions, dense matter, and chaotic turbulence everywhere, many of the signals astronomers rely on would be impossible to detect. Instead, the immense emptiness between stars and galaxies allows information to travel across cosmic distances with remarkable clarity. The universe may appear silent, but its signals remain intact. Astronomical instruments are therefore designed with extraordinary precision. Telescopes must remain stable while tracking objects that move slowly across the sky. Detectors must be cooled to extremely low temperatures to prevent thermal noise from overwhelming faint cosmic signals. Even the location of observatories is chosen with care. Remote mountaintops, desert plateaus, and space-based observatories far beyond Earth's atmosphere all help reduce interference. In these quiet environments, astronomers can detect signals that have traveled across billions of years. A photon emitted by a distant galaxy may arrive at a telescope after an unimaginably long journey. And when it does, it becomes part of humanity's effort to understand the cosmos. This effort reflects something remarkable about the species that inhabits a small planet orbiting an ordinary star. Despite living in a universe that is vast, quiet, and often indifferent to human concerns, people have developed the ability to observe and interpret signals arriving from across cosmic distances. Instruments built on mountain tops and launched into orbit now collect information about events that occurred billions of years before Earth even existed. Through careful measurement and patient observation, astronomers continue to decode the messages carried by light and radio waves traveling through the silent depths of space. The calmness of the universe, once interpreted as emptiness, becomes an opportunity for discovery. It allows the faintest signals to survive long journeys across the cosmos, and it allows observers on a small world to study the vast universe that surrounds them. From these observations emerges a deeper reflection, a realization that cosmic silence is not merely a physical condition of the universe. It is also a setting in which conscious beings have arisen, capable of asking questions about the nature of reality and their place within it. And those questions lead naturally toward the broader meaning of living in a universe that is both immense and remarkably quiet. When the universe is viewed from the scale of human experience, quietness can feel surprising. Earth is rarely silent. Wind moves through trees, oceans crash against coastlines, and living creatures constantly interact with their surroundings. Even the atmosphere itself hums with motion and energy. Sound and activity are ordinary parts of life on this small planet. Yet the wider universe operates under very different conditions. Space stretches across distances so immense that even powerful cosmic events become widely separated from one another. Galaxies drift through vast volumes of emptiness, and the interactions between stars occur slowly, often unfolding across millions or billions of years. From this perspective, the calmness of the cosmos begins to make sense. Quietness is not a sign that nothing is happening. Instead, it reflects the extraordinary scale on which the universe operates. Gravitational physics plays a central role in shaping this calm structure. Gravity is the force that gathers matter together to form stars, galaxies, and clusters of galaxies. Yet gravity also works gradually and patiently. It does not usually produce sudden or chaotic motion across large distances. Instead, gravitational attraction slowly organizes matter into stable systems. A cloud of gas collapses gently over millions of years to form a star. Galaxies rotate in graceful patterns around their centers. Clusters of galaxies drift together through space under mutual gravitational influence. These motions are powerful, but they unfold slowly. The result is a universe where large-scale order emerges from countless gravitational interactions, occurring over immense spans of time. Instead of constant turbulence, the cosmos settles into patterns that remain stable for billions of years. Galactic disks rotate steadily. Planetary systems orbit predictably. Even galaxy clusters follow paths shaped by gravity across the cosmic web. The apparent stillness of the universe therefore arises not from inactivity, but from stability. Physical laws encourage matter to organize itself into structures that persist over long durations. Once those structures form, they often remain remarkably calm. In this sense, cosmic quietness reflects a kind of balance. Energy continues to move through stars and galaxies, yet the immense scale of space spreads that activity across such large distances that the universe appears tranquil when viewed from afar. Some scientists have reflected on this calmness not only as a physical property of the cosmos, but also as a source of philosophical insight. The physicist Freeman Dyson often wrote about the long-term future of the universe and the role of intelligence within it. Dyson believed that life and consciousness might adapt creatively to the evolving conditions of the cosmos, even as stars fade and galaxies grow quieter. His reflections emphasize the idea that the universe provides both challenges and opportunities for thinking beings. The quietness of space may seem intimidating at first, but it also creates an environment where delicate signals can travel undisturbed across vast distances. In many ways, that stillness makes astronomical discovery possible. If the cosmos were crowded with constant collisions and chaotic noise, the faint signals astronomers rely on would quickly vanish. Instead, the calmness of space allows light to travel for billions of years without losing its message. Each photon that reaches a telescope carries information about the place and time where it originated. A faint signal arriving today might reveal the structure of a galaxy formed billions of years ago. Another might reveal the explosion of a distant star that occurred long before Earth existed. These messages cross the universe quietly, yet they contain extraordinary stories. Cosmic silence therefore invites curiosity. The night sky appears calm, but careful observation reveals hidden layers of activity unfolding across enormous scales. Beneath the stillness lie the births and deaths of stars, the collisions of neutron stars, the growth of galaxies, and the slow expansion of the universe itself. All of it continues, even while the sky appears peaceful. This contrast between apparent stillness and underlying activity has fascinated scientists and philosophers alike. It reminds observers that human senses provide only a limited view of reality. What appears silent may still be filled with signals. What appears empty may still contain structure and energy. The universe quietly invites investigation. Freeman Dyson once suggested that scientific exploration is partly an act of learning how to listen more carefully to nature. Telescopes, detectors, and observatories extend human senses far beyond their natural limits. Through them, astronomers detect faint traces of radiation, gravitational waves, and subtle patterns in the cosmic microwave background. Each discovery reveals another layer of the universe hidden within the calm appearance of the night sky. The stillness of the cosmos, therefore, becomes a source of wonder rather than emptiness. It provides the conditions that allow light to travel, signals to survive, and knowledge to accumulate across generations of observers. In a universe filled with turbulence everywhere, such delicate information might never reach us. Instead, the immense quietness of space allows a small world orbiting an ordinary star to receive messages from across billions of years of cosmic history. Seen in this light, the calmness of the universe becomes something beautiful. It reflects the deep order emerging from fundamental physical laws. Gravity shapes galaxies. Thermodynamics guides the flow of energy. Cosmic expansion stretches space itself. Together, these processes produce a universe that evolves slowly, steadily, and often quietly across unimaginable timescales. Within that vast calm, stars shine, galaxies rotate, and light travels patiently across the depths of space. And on one small planet, observers look upward and begin to understand the story written in that quiet sky. The realization that cosmic silence emerges naturally from the structure of the universe brings the narrative full circle. What once seemed like emptiness becomes a consequence of scale, physics, and time. The universe is not silent because it lacks activity. It is silent because its events are separated by distances so vast that their energies rarely overlap. Quietness, in other words, is the natural voice of a universe that is unimaginably large. And within that stillness lies a story that stretches from the earliest moments after the Big Bang to the distant future of stars, galaxies, and space itself. When people first imagine the universe, it is often pictured as dramatic and energetic. Exploding stars, colliding galaxies, powerful cosmic forces shaping the fate of entire regions of space. All of those things do exist. Yet when the night sky is observed with the naked eye, the overwhelming impression is one of calmness. The stars sit quietly against a dark background. The universe appears almost motionless. Nothing seems to be rushing or colliding on a visible scale. Understanding why the cosmos appears so quiet requires looking carefully at several fundamental features of the universe itself. One of the most important explanations lies in the sheer size of space. The distances between stars, galaxies, and clusters of galaxies are enormous. Even the nearest star beyond the Sun, Proxima Centauri, lies more than 4 light-years away. That means the light reaching Earth from that star began its journey more than 4 years ago. When distances stretch across such scales, interactions become rare. Stars rarely collide with one another. Galaxies may pass through one another only once in many billions of years. Even powerful cosmic explosions occur so far apart that their effects remain isolated. Distance spreads activity across the universe, it dilutes energy, and from a distant perspective the result is quietness. Another crucial factor involves the physics of sound and matter. Sound waves require a medium such as air, water, or solid material to travel. On Earth, sound moves through vibrating molecules that push against one another. But interstellar space contains extremely little matter. In many regions of the galaxy, only a few atoms occupy each cubic centimeter. Without a dense medium, sound waves cannot propagate across cosmic distances. Explosions that would produce deafening noise on Earth occur silently in the vacuum of space. The universe therefore lacks the conditions required for sound to travel. Yet this does not mean that the cosmos is inactive. Instead of sound, the universe communicates through electromagnetic radiation. Light, radio waves, infrared radiation, and other forms of electromagnetic energy move through space without requiring a material medium. The work of James Clerk Maxwell during the 19th century revealed how oscillating electric and magnetic fields can travel through empty space as waves. These waves carry information across the universe. Stars shine by emitting light produced through nuclear fusion. Galaxies emit radio waves from energetic particles moving through magnetic fields. Black holes generate radiation as matter spirals inward through accretion disks. Signals travel constantly through the cosmos. They simply arrive as light rather than sound. Astronomical observatories have become the tools that allow scientists to detect and interpret those signals. Facilities such as the European Southern Observatory, the Atacama Large Millimeter Array, and the Square Kilometer Array are designed to capture extremely faint electromagnetic radiation arriving from distant regions of the universe. Space-based instruments extend this capability even further. The James Webb Space Telescope observes infrared radiation from galaxies formed billions of years ago. Earlier missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite mapped the cosmic microwave background radiation left over from the early universe. Each observatory acts like a sensitive receiver tuned to a different part of the electromagnetic spectrum. Through these instruments, astronomers detect signals that would otherwise remain invisible. These signals reveal that the universe is far from empty. Supernova explosions release enormous bursts of energy when massive stars collapse. Neutron stars collide, generating gravitational waves detected by the Laser Interferometer, Gravitational Wave Observatory, through the pioneering work of scientists such as Rainer Weiss and Kip Thorne. Magnetars unleash intense flares of radiation produced by powerful magnetic fields described in theoretical models developed by Robert Duncan and Christopher Thompson. Even the faint glow of the cosmic microwave background radiation carries information about the conditions that existed when the universe was only a few 100,000 years old. These discoveries show that the quiet appearance of the cosmos does not mean that nothing is happening. Instead, activity occurs across enormous distances and timescales. Events that appear dramatic locally become subtle when spread across billions of light years. Cosmic expansion adds another layer to this quietness. The discovery of the expanding universe by Edwin Hubble revealed that galaxies are drifting apart as space itself stretches. Later observations by Saul Perlmutter, Brian Schmidt, and Adam Riss demonstrated that this expansion is accelerating due to the influence of dark energy. As galaxies move farther apart, interactions between them become even less frequent. Clusters of galaxies gradually separate. The universe grows more spacious. And over time, cosmic activity becomes increasingly isolated. Thermodynamics also contributes to this trend. The work of Ludwig Boltzmann established that physical systems tend to evolve towards states of higher entropy, where energy becomes more evenly distributed. Stars convert nuclear fuel into radiation that spreads outward through space. Black holes eventually evaporate through Hawking radiation. Energy disperses across ever larger volumes of the universe. This gradual spreading of energy leads to a calmer cosmic environment. Over immense stretches of time, the universe moves towards states where interactions become rarer and structures become more widely separated. Seen from this perspective, cosmic quietness emerges naturally from several fundamental properties of the universe. Vast distances reduce interactions. Vacuum conditions prevent sound from travelling. Electromagnetic radiation carries signals instead of pressure waves. Cosmic expansion spreads galaxies farther apart. Thermodynamics gradually disperses energy across larger regions of space. Together, these factors create a universe that appears calm, even while extraordinary events unfold within it. What seems silent at first glance becomes rich with hidden activity once the correct instruments and theories are applied. Astronomers have learned to listen carefully to the faint signals arriving from across cosmic distances. Every photon captured by a telescope carries information. Every radio pulse reveals something about the physics of distant stars. Every gravitational wave detection tells the story of massive objects colliding far beyond the Milky Way. The universe may look quiet, but it is constantly communicating. Understanding that quietness requires recognizing that human senses evolved for life on a small planet, not for observing phenomena spread across billions of light years. Once instruments extend those senses, the silent sky becomes filled with signals waiting to be interpreted. The calm appearance of the cosmos therefore becomes a reminder of its scale, a scale so vast that even the most powerful events are separated by distances that soften their presence. And that realization naturally leads toward a final reflection, not only about the physics of cosmic silence, but about what it means for conscious observers to exist within such an immense and quietly unfolding universe. The universe often gives the impression of quietness. On a clear night the sky appears still. The stars shine steadily, distant and calm, scattered across a dark background that seems almost empty. Nothing appears to move. Nothing appears to change. Yet that stillness is only the surface of a far deeper story. Across the cosmos, stars are constantly being born and dying. Galaxies drift through enormous gravitational structures. Black holes swallow matter while launching jets of energy across intergalactic space. Neutron stars collide with such violence that they ripple the fabric of space-time itself. The universe is not silent because nothing is happening. It appears silent because everything is happening across unimaginable distances. Cosmic scale changes how activity is perceived. When events are separated by millions or billions of light years, their energy spreads across vast volumes of space. Explosions that would be deafening nearby become faint flashes of light by the time their signals reach distant observers. Space itself also plays a role. The vacuum between stars contains almost no matter, preventing sound from travelling in the way it does on Earth. Instead of vibrations moving through air, the universe communicates through electromagnetic radiation. Light carries the story of the cosmos. Every photon arriving at a telescope represents a message from somewhere in the universe. Some of those messages began their journey billions of years ago, travelling patiently across expanding space before finally reaching Earth. Through those faint signals, astronomers have learned to reconstruct the history of the universe. The cosmic microwave background radiation reveals a snapshot of the universe when it was only a few 100,000 years old. Radio telescopes detect pulsars spinning rapidly in distant regions of the Milky Way. Space telescopes observe galaxies that formed when the universe itself was young. Each discovery reminds us that the calm appearance of the night sky hides immense complexity. Even the large-scale structure of the universe contributes to its quiet nature. Gravity gathers matter into galaxies and clusters, while leaving vast regions of space nearly empty. Cosmic expansion slowly carries those structures farther apart over time. The result is a universe where activity exists, but where enormous distances separate one event from another. The quietness of the cosmos therefore emerges naturally from its structure. Physical laws shape the distribution of matter and energy across space. Thermodynamics spreads energy outward, encouraging systems to move toward equilibrium. Gravity organizes matter into stable structures that persist for billions of years. Together, these processes create a universe that evolves slowly and often calmly, and yet that calmness has provided a remarkable opportunity. Because the universe is so spacious and quiet, delicate signals can travel enormous distances without being destroyed. Light from distant galaxies survives journeys lasting billions of years. Subtle fluctuations in background radiation preserve information from the earlier stages of cosmic's history. Without this quietness, much of that information would never reach us. Astronomy therefore becomes an act of listening. Telescopes, detectors, and observatories extend human senses far beyond their natural limits. They capture faint signals from across the universe and translate them into knowledge about the nature of reality. Through careful observation and patient analysis, humanity has learned to interpret the messages carried by light. The night sky that once seemed silent now appears filled with stories. Stories of stars forming within cold clouds of gas. Stories of galaxies evolving across cosmic time. Stories of the early universe preserved in faint radiation that still fills all of space. The quietness of the cosmos no longer represents emptiness. It represents scale. A scale so vast that the most powerful events unfold gently when viewed from afar. Standing beneath the night sky, it is easy to feel that the universe is distant and silent, but the truth is more remarkable. The cosmos is constantly speaking. Its voice arrives in the form of light that has travelled across billions of years, carrying information about places far beyond human reach. And on a small planet orbiting an ordinary star, observers have learned how to listen. In that quiet sky, the universe is not silent at all. It is simply waiting to be understood.